Hello, solubility product time. This is dealing with the equilibrium situation, how things change with a common ion. Here we've got gym chalk. Those of you who are rock climbers, weightlifters, gymnasts, rub this stuff on your hands, and the white powder reacts with water to make a hydrate. So the water on your hands is removed and they're nice and dry. The material, magnesium carbonate, is non-toxic unless you chew on it, eat quite a bit of it. Then it's a laxative, so don't eat your gym chalk. The reaction is magnesium carbonate. If you dump it into water, it will dissolve a little bit. I mean, you don't want to dissolve a lot because then you just have so it hardly dissolves at all. It dissolves to make some magnesium ions and carbonate ions. The magnesium ions are the ones that act as the laxative. So if you dump some of this stuff into a beaker of water, these ions will dissolve a little bit of the white powder will dissolve, and the concentration of magnesium times the concentration of the carbonate ions will end up in molarity, will produce 4.49 times 10 to the negative 5. Let's see what that value is in terms of molar concentration. Here's the original equilibrium, 6.7 millimolar, 6.7 millimolar, and it multiplies out to make our Q. We've got KSP, and that's the limit. Everything's in equilibrium. A little bit of magnesium carbonate dissolves, precipitates, a little bit of this stuff dissolves, and you don't see any changes. Now, if you add some magnesium nitrate's soluble, very soluble, as all nitrates are, you can soup up the magnesium concentration to a laxative level, 100 millimolar, and that's going to produce an ion product of 6 times 10 to the negative 4. That's like over 10 times more concentrated than it should be. So our Q is greater than our KSP, and we follow the little alligator, and this reaction is going to go backwards. It's going to have a reverse reaction. The magnesium is going to go back into the magnesium carbonate, but it can't do that without taking carbonates with it. So this innocent bystander, carbonate, says, oh, I used to be okay, but the magnesium is messing things up. So now we've dropped both of these, and they both have to decrease equally. But still, our ion product is too high, so back to the drawing board. We're going to have to take out more magnesium and the innocent bystander carbonate, and more magnesium and carbonate, and more magnesium and carbonate. And we keep on going and going and going on this spreadsheet until finally, you're getting close. We're at 10 to the negative 5 right now, but still a little bit higher than we expect. And finally, when we end up getting our new equilibrium, 0.0943, magnesium is still pretty high in concentration, but the carbonate's been wiped out down to 0.5 millimolar in order to satisfy our Q's equal to our KSP and to get a new equilibrium. This is when the precipitate stops. Both of these things had to decrease in their concentration by 5.7 millimolar, but there wasn't that much carbonate to start off with. But that's the way solubility goes. The common ion is going to be decreased, but the innocent bystander, the anion, the carbon in this case, was really, really wiped out. But you can't have a ion product any bigger than the KSP. That's why they call it the limit. That explains the reaction and why both the magnesium and the carbonate have to decrease, and the entire thing about solubility. You get some complications when there are coefficients. So, solubility product, there we go.